So today we're going to talk about molecular polarity and shapes. First of all, I'd like to remind you of these electrostatic potential maps that we looked at before. Red represents the most negative, and blue represents the most positive electrostatic potential. A nonpolar molecule has no net dipole. So take a look at this hydrogen molecule here. This has no net dipole. It's very neutral. Molecules that are nonpolar do not exhibit dipole-dipole intermolecular attractions. So the dipole-dipole intermolecular attractions are going to happen with these two molecules that we see there. We looked at some other molecules. Here's a map of chloromethane. This is a chlorine up here, and these are hydrogens down here. So you can see it's more negative up at the top of the molecule here. Here's hexane. Hexane is completely neutral. It is a non-polar molecule. Water is polar. It has this negative area here. This is around the oxygen. We remember that that negative area comes because oxygen is winning the tug of war of electrons. There are also lone pairs up here. Ethanol and pentanol both have these oxygens just like this water that are winning tug of wars against other atoms. Let's take a look at both nonpolar and polar molecules. So here are three examples of nonpolar molecules. The first one is CCl4. And you can see here, here's the electrostatic potential map. It's all green. It is a nonpolar molecule. Another example of a nonpolar molecule is CO2. Now, at first glance, you might think, well, oxygen is going to win the tug of war against carbon. So oxygen is going to be more electronegative and therefore more negative, but it's even on both sides. So it pulls evenly on both sides of the molecule. So this is an overall nonpolar molecule. And then we've got oxygen bonded to another oxygen. You probably could have guessed. These are sharing electrons evenly. It is a nonpolar molecule. Here are the polar molecules, right? HCN. N is going to pull electrons towards it. It's going to be very negative on this end. Here, very similar to CCl4, HCl3. So instead of having 4 Cls, we have an H up here. This becomes a polar molecule because there's something different attached to it. And then this one, of course, water is our poster child for polarity. Oxygen is pulling electrons towards it, as well as the lone pairs that are up there. Now, one of the things that you might have noticed were shapes. What is up with these shapes? Why are some things bent and some things in lines and some things in these weird shapes? What is up with those shapes? What do they mean? So take a look at this video.
What is the shape of a molecule? Well, a molecule is mostly empty space. Almost all of its mass is concentrated in the extremely dense nuclei of its atoms. And its electrons, which determine how the atoms are bonded to each other, are more like clouds of negative charge than individual discrete particles. So a molecule doesn't have a shape in the same way that, for example, a statue has a shape. But for every molecule, there's at least one way to arrange the nuclei and electrons so as to maximize the attraction of opposite charges and minimize the repulsion of like charges. Now let's assume that the only electrons that matter to a molecule's shape are the outermost ones from each participating atom. And let's also assume that the electron clouds in between atoms, in other words, a molecule's bonds, are shaped kind of like sausages. Remember that nuclei are positively charged and electrons are negatively charged. And if all of a molecule's nuclei were bunched up together, or all of its electrons were bunched up together, they would just repel each other and fly apart, and that doesn't help anyone. In 1776, Alessandro Volta, decades before he would eventually invent batteries, discovered methane. Now, the chemical formula of methane is CH4. And this formula tells us that every molecule of methane is made up of 1 carbon and 4 hydrogen atoms. But it doesn't tell us what's bonded to what or how the atoms are arranged in 3D space. From their electronic configurations, we know that carbon can bond with up to 4 other atoms, and that each hydrogen can only bond with 1 other atom. So, we can guess that the carbon should be the central atom, bonded to all the hydrogens. Now, each bond represents the sharing of 2 electrons, and we draw each shared pair of electrons as a line. So now we have a flat representation of this molecule. But how would it look in 3 dimensions? We can reasonably say that because each of these bonds is a region of negative electric charge, and like charges repel each other, the most favorable configuration of atoms would maximize the distance between bonds. And to get all the bonds as far away from each other as possible, the optimal shape is this. This is called a tetrahedron. Now, depending on the different atoms involved, you can actually get lots of different shapes. Ammonia, or NH3, is shaped like a pyramid. Carbon dioxide, or CO2, is a straight line. Water, H2O, is bent like your elbow would be bent. And chlorine trifluoride, or ClF3, is shaped like the letter T. Remember that what we've been doing here is expanding on our model of atoms and electrons to build up to 3D shapes. We'd have to do experiments to figure out if these molecules actually do have the shapes we predict. Spoiler alert, most of them do, but some of them don't. Now, shapes get more complicated as you increase the number of atoms. All the examples we just talked about had one obviously central atom, but most molecules, from relatively small pharmaceuticals all the way up to long polymers like DNA or proteins, don't. The key thing to remember is that bonded atoms will arrange themselves to maximize the attraction between opposite charges and minimize the repulsion between like charges. Some molecules even have 2 or more stable arrangements of atoms, and we can actually get really cool chemistry from the switches between those configurations. Even when the composition of that molecule, that's to say the number and identity of its atoms, has not changed at all.
So, as we take a look at these different shapes, I wanted you to keep in mind that, like he said in the video, you can have big, long, huge chains of things, and they contain pretty much these little shapes within them. So let's think back to what we were looking at before. What determines if a molecule is polar? Okay, we know if a bond is polar because we know that bond polarity has to do with electronegativity. We've already talked about that. But what determines if a molecule is polar? Well, first of all, if you just have one bond in the molecule, then the bond polarity is the molecular polarity. This is a polar bond and therefore a polar molecule. But if you have more than one bond, you need to look at a few things. The first thing you need to look at is the shape. If there are lone pairs on the central atom, like in the case of water, and this is NH3 or ammonia, if you have lone pairs on the central atom, it will be polar. We can guarantee that. That's because those lone pairs make a cloud of negative electron charge. If it does not have lone pairs, then we look at something secondary. We look at symmetry. So, for example, here's CCl4, that is nonpolar. It is all symmetrical. And here's CClH3, that is polar. That Cl is pulling more towards it. I'll show you another example with what we just looked at. Here, this is linear. It's even on both sides, so it's nonpolar. This is also linear. It is not even on both sides, so that is polar. So it is the shape and the symmetry we need to look at for molecular polarity. And when we talk about shape, this has a special name. It's called VESPER, and I know it doesn't look like it's pronounced, but it stands for valence shell electron pair repulsion. And it says that orbitals try to spread out as much as possible. So let's see what this guy says about VESPER.
After you've mastered how to write electron dot formulas on a piece of paper, which is a flat sheet and we're kind of limited to the two-dimensional world, you have to really start thinking about how molecules really look in a three-dimensional world, because that's the world that molecules actually live in. The simplest model for modeling this type of behavior, and it actually works rather well, is called the valence shell electron pair repulsion theory. And the name's probably scarier than it actually is as far as it works. We often just call it the VSEPR theory, and then we kind of just say it all together, VSEPR theory. So you'll hear me say VSEPR theory from now on when I mean the previous. So the way it works, and the name kind of gives it away, is you take your electron dot formula and you simply count electron regions around the central atom, and you realize that each of those regions is a negatively charged region. And so it's going to repulse all the other negatively charged regions, and they're going to try to get away from each other. They can't completely get away, though, because the nucleus of the central atom is holding them in. So what they do is they try to get away from each other, but they're still held by the central atom. This leads to distinct molecular shapes. And the easiest one is two regions. If you only have one atom on one side and one on the other, and they try to get away from each other, you get a fairly linear type molecule. And so that's the first one. Two regions gives you linear shape. The bond angle is 180. Stepping up to the next one, three regions. You count the regions around the central, there's three. If three regions try to get away from each other, you basically get a nice kind of pie shape. It's like taking a pie and cutting it into perfect thirds. So you get a 120-degree angle all the way around for those three regions. Both of those regions are still planar. They still look just fine on a sheet of paper. It's when you get to four regions that you have to go to the third dimension. You have to go three-dimensional. And what this gets you is a shape that we call a tetrahedron or tetrahedral geometry. It's four regions around a central, all perfectly symmetric. And if you take a look and spin the molecule around and look at it, every region is equivalent. And the bond angles are now down to 109.5 degrees. That's a tetrahedral geometry. So as you can see, the bond angles are getting smaller because we're bringing in more regions. We started at 180 for linear, 120 for trigonal planar. Now we're down to 109.5 for tetrahedral. So that really sums up most of what we will use, especially in organic chemistry.
So we talk about bonded and unbonded domains. Okay, unbonded electron domains, we call those lone pairs. Those are electrons that are not bonded to any other atom. And I showed you them before and I told you they were important. Well, they're the reason that water bends and that NH3 is bent down like a pyramid. These unbonded electrons, even though we don't write them a lot of times, chemists know they're there and they are making negative charges. The bonded domains are the shared electron pairs between the atoms. So if all four of four electron domains or things around the central atom are bonded and there are no lone pairs, we call this a tetrahedral shape. And a good example of a tetrahedral shape is CH4. There's 109 degrees between the bond angles. It's trying to spread out as much as possible. If you have four electron domains and there is one lone pair, that one lone pair exists up here, we call that a pyramid. That's like NH3. And then if you have two lone pairs and there are still four electron domains or four things bonded to the central atom, that's bent. That's water, H2O. So let's look at what happens if you have three electron domains or three things around the central atom. If you have zero lone pairs, then you have something called a trigonal planar. Now this example is BH3. We have not talked about it, but boron is happy with only 6 valence electrons. It doesn't matter whether these are double bonds or single bonds. If there are only three things around the central atom and no lone pairs, we call that a trigonal planar shape. And the bond angle between those are 120. And then there's a second type of bent. This is bent at 120 degrees. This is when you have three things around the central atom and one lone pair. And if you have two electron domains, it is always linear. So CO2, you'll notice here in this picture, it doesn't even show the double bonds, but that's going to be linear. That's kind of the only choice for that. So here are the different shapes that we talk about in this class. We only talk about 2, 3, and 4 electron domains. When you get to AP, you can talk about 5 and 6 electron domains, and you can talk about all these shapes. But these are the 6 basic shapes that I want you to know about. The tetrahedral shape, trigonal planar, bent, at 109 degrees. Trigonal, or I'm sorry, this is trigonal pyramid, a pyramid shape. This is trigonal planar. This is bent at 120 degrees, and then of course, linear. So take a look at this, pause the video, and determine the shapes of the following molecules. How did you do? Were you right? This first one is linear. This is trigonal planar. There are three things, no lone pairs. This is our tetrahedron. This is going to be in a lot of places that have to do with carbon chemistry. This is pyramid or trigonal pyramidal. And this is bent. And we don't actually know if this is bent at 120 or 109. Doesn't really matter, I guess, at this point. Now let's look back at molecular polarity practice. Determine if the following are polar or nonpolar, okay? The first one just has one bond in it. So if the bond is polar, the molecule is polar. If the bond is nonpolar, the molecule is nonpolar. So this is a nonpolar bond because there's an even tug of war on electrons. This one, it's bonded to all the same thing, but it has lone pairs on the central atom. Therefore, it has to be polar. That's because this molecule has this negative charge up here that's pulling electrons, or it has a charge of a negative charge up here. This nitrogen is pulling electrons towards it, but those electrons are what's making it very polar. And then finally, CH4, there's no lone pairs, and it's all bonded to the same thing. This is a nonpolar molecule. Nonpolar, polar, nonpolar. Now, don't forget about bond polarity, right? Molecular polarity is looking at the whole molecule. It's different than individual bond polarity. Nonpolar molecules can contain polar bonds, and polar molecules can contain nonpolar bonds. A molecule that has all nonpolar bonds is automatically a nonpolar molecule. For example, hexane, or in this case, butane, are hydrocarbons. They're just C's and H's. We're going to consider those nonpolar. The polar bonds in a molecule can cancel out if the central atom has no lone pairs. That's to say that all the bonds are the same, okay? The shapes that this can occur in are linear, tetrahedral, and in this case, in this picture, trigonal planar. So this may have three polar bonds, but they're pulling all evenly and there are no lone pairs. So this is a non-polar molecule. If you care, there's a little bit of gray area about this. For example, NCl3 and PH3 are very slightly polar and sometimes can be called nonpolar because they are comprised of all nonpolar bonds. But NCl3 has those electrons on the central atom, so it is very slightly polar, okay? But we're not going to split hairs about this. It's more important to me that you understand the concept as a whole. So one more time, give the shape of these molecules and determine if the molecule is polar, nonpolar, and describe any IMAs or intermolecular attractions that are present. So here's PH2Cl. On a test, you might need to know how to draw that. CH2O2, again, you need to know how to draw it. SO2, H2, NH3, CH4, H2CO, HNO. So go ahead and pause the video and see if you can figure those out. And